Friends of BSc second sem, somewhere I have mentioned that kinetic theory of gases is I have divided into three parts. Already we have discussed in depth first two parts. The first part is Maxwell's law of distribution of velocities and certain velocity terms, the derivations, experimental verification we have discussed in detail. The second part is transport phenomena in gases on the basis of kinetic theory of gases. We have discussed in general the transport of, say, momentum, transport of mass and transport of energy. Momentum gave us the result or the viscosity expression. Energy, transportation of thermal energy gave us what is called as thermal conductivity, coefficient of thermal conductivity, and the transportation of mass results or gives rise to, say, diffusion coefficient. This we have discussed as a second part. What is remaining in third part of kinetic theory of gases is Brownian motion. I have written here Brownian motion. Brownian, the name Brownian, Brown is a name of a person, a scientist. Basically, he was botanist. He discovered motion known as Brownian motion. This motion is named after him. Now the question arises here, what is the relation between the subject physics and the botanical concept called as Brownian movement or Brownian motion? See, people, they have studied Brownian motion. What is meant by Brownian motion? Let us discuss first, and then let us establish the Brownian motion and the kinetic theory of gases. What is the basis for it? Why a term Brownian motion basically comes in life sciences. We are studying here in physical sciences. Okay, let me answer it little later. So the Brownian motion was first observed by a Brownian, a British scientist, in the year 1872. What he was observing, what he was studying? He studied pollen grains or spores which are immersed in a solution called as maybe water or any other solvent here. When the pollen grains or spores, known as spores, spores, they are mixed with solvent like water, and then he observed the pollen grains, the movement of pollen grains under a ultra microscope or microscope. What he has observed, that the pollen grains mixed with water, they have the random motion. He observed the motion of the pollen grains under ultra microscope in his laboratory, he found certain interesting things, that the pollen grains forever they are in motion, hours together, days together, years together. He observed that the pollen grains in a solvent, they are moving in a haphazard manner. The pollen grains, they sink, they rise, they spin, again they sink. So that movement he has observed, and this movement of pollen grains under a solution, solvent, for example water, he observed that this motion is haphazard, random and forever. This motion, what he has observed, is perpetual and spontaneous. People have tried with a different colloidal solution. We know the paint which we call the colloidal solution, the emulsion paint. In that solution or emulsion paint, or in generally we call it as colloidal solution, when the colloidal solution, colloidal particles are mixed in a solution, we call it as colloidal solution. That colloidal solution, when it is observed, the similar kind of situation what I have explained using an example of pollen grains is observed, and the motion here is haphazard, non-stop motion, random motion, and the motion is observed forever. So this is another example. So if you take, say, air mixed with smoke particles, normally when heavy vehicle is moving, it has exhaust, and the exhaust is a smoke which gets mixed in air. The smoke has particles, smoke particles, and those smoke particles moment they enter into, or what is called as gets diffused into air, the gaseous medium. These particles of smoke, they are granules, very small in size, and those particles they get diffused and they may move here and there with a haphazard motion itself, random motion itself. To get a common example, say a room with fresh air, and said there is no opening, only one opening, that one window is open, and some dust particles, say spray of dust particles enter into the room. So the dust particles may be mud particles. Dust means anything here, unwanted thing, small particles which we can see them, even we inhale them, dust particles. Many times we call it as polluted air, and it is very dangerous to our health also. So when the dust particles mixed with a silent, say stable air, the dust particles, they have the movement, and if you observe that under microscope, you can see the dust particles, you can observe them, a bright, say spot, shiny spot, and those spots or particles, dust particles, they move randomly, they move haphazardly, they get mixed, they sink, they spin, they rise, and that haphazard motion goes on, and it is spontaneous, it is perpetual, it is a non-stop haphazard motion. And this non-stop haphazard motion Here we call it as Brownian motion. Well, what are the features of this Brownian motion? Motion of each particle. I will give you, before I start, I will give one more example here. You have seen fish pond or fish bowl. You take, people they say rare what is called as fish, and they keep the alive fish in a pond. We call it as fish pond or fish bowl. So when the fish bowl containing water, so it is without fish initially, it is calm and quiet. If you have a tiny fish, say showcase fish, different color, if you live into it, that fish forever, it moves, swims, goes down, comes up, and it breathes inside the bowl. So the Brownian particle known, the dust particle or immersed particle, dispersed particle in a solution is known as Brownian particle, and the motion of Brownian particle is spontaneous, perpetual, it is non-stop, and it is forever. So you can have many more examples, not only pollen grains, but many more examples of Brownian motion. Well, what is the basis or what is the future? What is the future of this Brownian motion? I'll write one by one, and then basis we'll see. Motion of each particle known as Brownian particle is completely irregular. It is not regular motion. It is completely irregular and random. No two particles can execute the same type or same motion. It's impossible. No two particles can have the same type of motion. This is one of the features of this Brownian motion. Motion is continuous and takes place forever. This is another feature. Motion is continuous and takes place forever. Well, the smaller particles of colloidal solution, suspended particles in the medium, to be more agitated compared to the larger size particles. We'll find the reason why the larger size particles cannot have the Brownian motion. This non-stop, absurd, random motion is called as Brownian motion, and the particle which executes this motion, suspended particle in a solution, is called as Brownian particle. Time being here for our reference. Smaller particles, smaller size particles, they will be more agitated than the larger particles. Motion is independent of nature of suspended particle, whether it is dust particle, whether it is smoke particle, whether it is say paint particle, whether it is pollen grain. It doesn't depend upon the what type of particle it is. The motion is independent of nature of particles here. Well, the motion becomes more rigorous when the size of a particle is small, and the motion becomes more rigorous, more agitated when the temperature of the system, that is suspended particle, and the medium called as liquid medium is. The motion is more rigorous when the temperature of the system is increased. More the temperature, more will be the rigorous motion of particles known as Brownian motion. If you have a liquid in a container and say you are suspending some particles, insoluble particles called as Brownian particles, and if you shake that container very well, its motion doesn't stop, or there won't be any changes when you shake that solvent or immersed solution, suspended particles and the solution. That's another point to be noted about this. Now, it depends upon the viscosity of the liquid. The motion is more conspicuous, say very visible. Conspicuous means very attractive. The meaning of conspicuous word, very attractive, easily visible in lower viscosity liquids. Motion cannot be modified by shaking, say what is called as containing liquid here. What is the basis of this Brownian motion and why we, the physics students, teachers, study this concept? Brownian motion, basis for the Brownian motion. See, this Brownian motion is due to the bombardment of particles in dispersed particles by the molecules of the medium. Say pollen grains are the particles and liquid the medium. Moment we bombard or we insert those pollen grains, right, we mix them, then those pollen grains, if you observe under ultra microscope, they look like bright spot, shiny spot under ultra microscope, and they will be rising, sinking, right, spinning, and that motion continuous process, and it is forever process. Why? What is the basis for this motion? See, moment they immerse, bombarded, dispersed in liquid medium, molecules of the liquid, initially they will be having the motion. We have seen this process, what is called as transfer of energy by the convection method, not the conduction, convection. See, when we heat a water and if you sprinkle some, say, any colored powder in it, so the colored molecules are while preparing tea, you can see, if you observe, boil the water, keep the water on a gas or a heater, put some tea dust which is pinkish, say brownish in color. So moment the particles goes on heating, you can see the color is coming, the particles gets mixed with water. That means the suspended particles here are, say, dust, tea dust particles, and they get mixed in it. You can observe the motion, the hot particles goes down, and that is how a convection method is. So molecules of the medium, they bombard or they exert force on the dispersed particles. As a result, the suspended particles, they move with unbalanced force. There will be unbalanced force from all the sides on a particle, and that particle moves in a different direction with a different magnitude and direction. So its motion is, say, it sinks, rise, spins, and it continues. What happens when the larger particles are mixed or, say, suspended in a solution? Larger particles rarely exhibit the Brownian motion because the molecular medium, that is liquid medium in which particles are, say, suspended, mixed. So the molecules experience a force, and that force gets balanced. Force exerted, there will be force of attraction as well as repulsion on both, that is molecule, suspended molecule, and the molecules of the medium. Molecules of the medium, they exert force on the incoming particle there, so that force gets balanced, and therefore this Brownian motion is not that prominent, or it is not observed at all in case of larger size particle. Whereas the Brownian motion is more prominent, it is conspicuous, it is very attractive, and you can see it, observe it in a lab using a microscope prominently. And that motion you can see, you can observe in case of smaller size particle. What happens? The molecules of the medium in which the particles, suspended particles, are moving, the molecules of the medium exert forces on the suspended particles. That particles execute, say, force on the suspended particle, and that force becomes unbalanced, and it's not balanced, unbalanced, both in magnitude and direction. As a result, the particle moves in a random motion. What is the analogy between the Brownian motion and kinetic theory of gases? See, the motion of Brownian particle, a particle suspended in a colloidal solution, you can call it as Brownian motion, is similar to the molecules, motion of the molecules in gases. It is similar. When we apply the kinetic theory of gases, laws of kinetic theory of gases to the Brownian motion, we can study the same things. And therefore, laws of kinetic theory of gases are applied to the Brownian motion. And people have developed a theory. The first person was a Langevin, who has developed theory of Brownian motion. Later on, this problem is studied by the great Einstein. Einstein has observed Brownian motion and developed a theory based on two concepts. That is, from the irregular motion, Einstein gave the theory, or developed the theory on theory of translational Brownian motion particles, and this Brownian motion or Brownian particles tends to diffuse. He studied the diffusion coefficient, that is the diffusion coefficient already we have derived on the basis of transport phenomena. More or less same concept he has applied for a Brownian motion particles, suspended particles, and he developed theory known as Einstein's theory of Brownian motion. We are studying this Einstein's theory of Brownian motion. Well, to study this Einstein's theory of Brownian motion, Einstein tried to calculate or tried to determine the diffusion coefficient in two different methods. The first method he has adopted from the irregular motion of suspended particles, from irregular motion of suspended particles. This is one method. The second method he has adopted from the difference in osmotic pressure caused by differences in concentration. More or less, this is nothing but the transport phenomena in mass that causes or gives rise to diffusion coefficient from differences in osmotic pressure. Partial osmotic pressure this osmotic pressure is caused by differences in concentration of suspended particle. Concentration of suspended particle. Particles. Now, if we use here kinetic theory of gases, whatever the knowledge we have acquired from so far from our discussion, if we apply that, including transport phenomena and other thing, we can study the Brownian motion here, and therefore the Einstein's theory of Brownian motion and its derivation, we are studying it here. So this is, we have to study, that is Einstein's theory of Brownian motion. Well, to start with this Einstein's theory of Brownian motion, Einstein's applied two different methods or ways to find out coefficient of diffusion. For this, I will have an imaginary cylinder. I will take here, this is its x-axis, say, this is, say, x-axis. I will have an imaginary cylinder here, cylinder in a medium here. This is imaginary cylinder of NP, and say this is, say here, NQ, and the length of this cylinder, let us take it as delta from these two ends, P and Q. See, its cross-sectional area, AB, its cross-sectional area. This is, on this side, N1 is the concentration on one end and N2 is the concentration on the other end. We are considering the imaginary cylinder of length delta, P and Q are the ends of this, and say N1 is the concentration at the end P, N2 is the concentration of suspended particles at the other end Q, A is the cross-sectional area of this imaginary cylinder, and say D is the coefficient of diffusion. D is the coefficient of diffusion. Now imagine the particles are moving from left to right. Probably we have not derived this, but the mean free path which we have studied can be derived on the same basis here. The number of particles crossing the surface, this P surface, in time t to the right is given by, this is half, say N1, the concentration, cross-sectional area A into length of this imaginary cylinder, say delta. The number of particles crossing this P reaching to this A middle portion at given time t. Similarly, the number of particles moving from the opposite end, that is Q to P, in opposite direction will be equal to the same, that is half N2 here. N1 is greater than N2 or N1 is not equal to N2. The concentration is not same, it is different. So A, the cross-sectional area, delta, the length remains same. Now the excess number of particles crossing the middle layer. Excess number of particles crossing the middle layer, that is A of cross-sectional area A, will be to the right or to the left. It will be excess number of particles crossing the layer to the right, crossing say middle layer to the right is equal to say half. It's a probability half may go this side, half may go other side, that is N1 minus N2. We assume that N1 is greater than N2. A, the cross-sectional area into length of the imaginary cylinder. Now this we got it. That is the number of particles, excess number of particles crossing the middle layer in certain time interval to the right or left is given by this. Now we have defined the diffusion coefficient. The diffusion coefficient is given by, that is half N1 minus N2 A delta is equal to minus, that is D, the diffusion coefficient, dN by dx, concentration gradient, its time interval t into cross-sectional area A. Here dN by dx is known as concentration gradient, but this N2 minus N1 difference in concentration is given by, that is minus